If you haven't printed them and you intend on printing them, don't write all this down because you're just wasting your time. If you don't intend on printing it, write fast. Okay. Horizontal and vertical translations of functions. A transformation is an operation that moves or maps a figure from an original position to a new position. Transformations that we are going to consider are translations, reflections, and stretches. Now, the reason why it's so much more difficult this year than it was last year is because last year I would give you literally this equation and you tell me these three things. So if you just memorize the three things, you were golden, right? This year, or you could plug it into your calculator and see how it moved. Okay? This year we're going to have these little f's in there, which means this is a function, but if it has a little f in it, you can't plug it into your calculator. So you need to know your transformations and you need to know your stretches and everything without being able to just have to plug it in your calculator because you don't have that option. Okay? Little f means you can't plug it in. There's no little f in your calculator that you can press. Okay? So what that means is it's some sort of function that exists. Okay? The other thing we make you do is move graphs. We also make you come up with equations of stretched and transformed graphs. We also make you move points. We also make you take a moved point and move it back. So all these much more difficult transformations, correct, than we had in the past. All we literally did was ask you, okay, what's the vertical stretch, horizontal translation, and often it was a multiple choice and you could very much guess it. Okay, and it was 1 or 2 on a unit. This is a whole unit and it comes up the whole way through. Okay? So, in general, if you have this in the form y minus k equals f of x minus h, or y equals f of x minus h plus k, I always move everything over to this side, and that's what I'm going to do every single time. Even if it's over here, that's great. I'm going to add the k over and have it into this form. I always put it into y equals, because then you're not trying to remember, do I flip it, do I keep it, do I flip? You just always do the same thing every time, okay? Now, don't worry about these things under here because it kind of confuses a person a little bit if you look at these. The catch here is it says h is greater than, if h is greater than 0, so if this h is greater than 0, just the h, then this would remain x minus h, would it not? If the h was positive, that's what it's saying, then it would stay x minus h, wouldn't it? So you move to the right. And you move to the right because h is actually positive. We're only looking at what the h would be. Okay, so if you had y equals f x minus 3 plus k, let's say, your h is actually 3. So you're going to move 3 right. Because the formula has an embedded negative sign in it, does it not? So if I have y equals f of x plus 3 plus k, this would actually be f of x minus a what? To get plus 3. A negative 3 plus k. So what would my h be? Negative 3. So I move 3 left. So that's why you go in the opposite direction, because it has that embedded negative sign. Okay? So h is always in the opposite direction. Your horizontal translation is always the opposite of the sign because it has that embedded negative in it. Okay? Now, does the k have a negative in front of it? No, that's why you always do what the k is. So if you have y equals f of x minus h plus 7, then k is plus 7, is it not? Because there's no minus sign with it. So you would go 7 up. 7 up, huh? That wasn't even planned. Y equals f x minus h minus 7. You would go 7 down. Okay? Make sense? Okay. So now we have mapping. Mapping and replacement notation. So, if the graph of y equals f of x is transformed to the graph of y minus k equals f of x minus h, then the point xy is going to become this point. We need to know our mapping. You use mapping whenever you move a graph or you move a point. So we're going to use mapping whenever you move a graph or a point. Now, why would I say a graph? Well, a graph is just a whole bunch of what? Points. So technically, I could just say use mapping when you move a point, because a graph is just a whole bunch of points, is it not? So why would we use mapping? Well, mapping, you could take your original point and you just do the mapping to it and you'll get every new point. That's why mapping is helpful. Okay? Now, if the graph of y equals f of x is transformed, then we say that x becomes x minus h and y becomes y minus k. This is called replacement notation. So what you're doing is your normal function would be y equals f of x, correct? But they say in here that we're replacing y with y minus k equals f, and replacing x with x minus h. So we're replacing this with this. We're replacing this with that. Okay? It's much easier if we actually look at some examples than random just variables. Okay? So example, the graph of y equals f of x is transformed to this. So this is the original graph. It has a little f in it, so can we plug it into our calculator? No. So this is how they actually know if you know what you're saying or if you just plug in your calculator and match graphs, right? You no longer can just match a graph. They took that ability out. This graph is transformed to this. That's great. I will never write it in that form. I'm going to add the 2 over. So I'm going to get y equals f x minus 3 plus 2. So I'm going to move that 2 over every time. And I always want to get it into y equals. Okay? So for replacement notation, you'd have to keep it in this form. This form to this form is replacement notation because we're actually physically replacing the y and the x. So you wouldn't want to move the 2 over if you were doing replacement notation. Okay? So what did we replace the y with? We replaced the y with y minus 2. So that's why we wrote that. And we replaced the x with x minus 3. So that's why we wrote that. So the only time you would keep it with the y is if you did replacement notation. That's what you're replacing it with. All points will move 3 units up and 3 units right, sorry, and 2 units up. We agree? Because we look here. This is 3 to the right because it's the opposite of what that sign is, right? And this is 2 up because we take the same. We agree? So, mapping notation then. If our normal point was xy, our new point is going to be x, and then I said I moved 3 to the right. So my point was at x, I'm going to move it 3 to the right. How could I write that? X plus 3. And then my point was x and y, and now I'm moving 2 up. So then I write y plus 2. So that's why we get this. Does that make sense? And mapping is awesome, because if they give you an original point now, you'd plug the original point in for xy, plug it in for the xy here, and you have the new point, and you move on to the next question. If you have to draw a graph, you take all the old points, plug them in here separately each time, draw your new graph, move on. So mapping is the best way that if you're going to move a point or a graph. Okay? So we have the point 4, 6. It was on the graph of y equals f of x. So this is telling you, you have to read this thoroughly. They don't put any extra words in math. If they have a word, it's there for a reason. So we have the point 4, 6. It's on the graph of y equals f of x. So they're telling you this is an original point. It's not on the transformed graph. It's on the original graph because it's on the graph of y equals f of x. We agree? Then the point would become 7, 8. Is that true? Well, let's try it out. So our mapping says xy becomes x plus 3, y plus 2. And you might say, I don't need mapping, Lepp. It's easy. I just add 2 and add 3 and add 2. It's not hard. Now, it's not hard. But then I'm going to add some horizontal stretches and some reflections and a whole bunch of extra stuff. Then it becomes hard because you're multiplying by fractions and by negatives and adding a number. Okay? So we use mapping the whole time so we get used to it. Yes, right now it would be super easy. We're not going to stay this way. Okay? So do mapping anyways, even if you think it's easy, because we're getting into practice. All right? So we try our point. 4, 6. So x is 4, y is 6. So I'm going to plug that in. 4 plus 3. 6 plus 2. 4 plus 3, 7. 6 plus 2, 8. So we proved it, right? Yes, you could have just added 3 and added 2, for sure. But like I said, it's not going to stay that easy, right? Okay. So when we describe graphs, describe means words, like horizontal translation, vertical stretch, horizontal stretch. You need those words if it asks you to describe, okay? So we want to describe how the graphs of the following functions relate to this. Now you have to always look at what the heck they're relating it to, because this graph, yay, actually is nothing on it, correct? But I could actually have a transformed graph and then transform it. So they're not always just a graph with nothing on it, okay? So you really have to look at what the heck graph you're dealing with first off, okay? So the graph we're dealing with first off is just a basic graph, nothing has happened. If they give you this, you should be happy, right? Because any transformation is just a transformation. We always do our transformations in the form CERT. Stretches, reflections, translations. And the reason why you do them in this form, you guys, and in that order, is because that is actually order of operations. Stretches and reflections multiply by the variable, and then translations, addition and subtraction to the variable. Okay, so you're just doing order of operations, that's all. And today we're only going to have to do T. So our S and our R are going to be blank. Okay? All right. So, are there any stretches? No. Are there any reflections? No. Because there aren't going to be any, because we're in the translation lesson. Hey, done, blank, blank. T, are there any translations? Has anything changed? The Y is the same. The only thing that's changed is you have X minus 3. So what are we going to do? What is that? Horizontal or vertical? Horizontal translation. So I just do H of T because I'm lazy. Horizontal translation. 3 which way? Right or left? Right, because there's a hidden minus sign in here, correct? So H is actually just positive 3. We agree? So it's 3 right. Do we have a vertical translation at all? Is there anything at the back? No. We're done. So if it's with the X, it's horizontal. If it's not in the bracket with the X, it's vertical. Okay? So the next one, B. The 4 is back here. Is it with the X? No. We don't have a stretch. We don't have a reflection. Our translation, is this vertical or horizontal? Vertical translation for what? Up. Try C and D. Okay, so stretches, reflections, we don't have any. We have a translation, it's 8 what? Down, so it's what kind of translation? This one we have stretch, nope. Reflection, nope. Translation, yes. We have vertical translation, what? 4 up. And a horizontal translation, 7 left. Okay, what happens to the graph of y equals f of x? So we're looking at a basic y equals f of x. If the following changes are made, so we're going to replace x with x plus 2. So we're going to take this x here, we're going to huck it behind our heads, and we're going to take the x plus 2 and put it in its place. Okay, that's what replacement notation is. You replace it. You don't keep the x and add the x plus 2, you're replacing it. So we have y equals f of x. There's an x in here, right? I huck the x out and I replace it with x plus 2. What happened? Horizontal translation to left. Now I'm taking the y here and I'm replacing it with y minus 8. So I'm taking the y, I'm hucking it behind my head. I'm not keeping it in there, I'm throwing it away. And I'm replacing it with y minus 8 equals f of x. And then I like getting into y equals. So y equals f of x plus 8. Because if I leave it over there, you have to remember it's the opposite sign. So why wouldn't you move it over so that you always consistently have the same thing? Okay? So this is the vertical translation, 8 what? up. If you left it over here, you'd have to remember you have to do the opposite of it. That's just more work. So why wouldn't you consistently just do the same thing over and over? Move it over. Okay? The point 2, -3 lies on the graph of y equals f of x. We're moving a point. What are we going to use? Mapping. So first thing I'm going to do, it says it's on the graph of y equals f of x. So the graph hasn't been moved before. All the points on y equals f of x are xy. We want to state, so this point is on the original. That's what it's saying. This is an original point, right? State the coordinates of the image of this point under the following transformations. So I'm going to minus the 8 over. So that's 8 what? What does it affect, the x or the y? Y. So our mapping, our normal xy, is now going to become x, because the x, is there anything in this bracket with the x? No. If the x in its bracket is by itself and it's just an x, nothing affects the x. So if it's in the bracket, it affects the x. If it's outside the bracket, it affects the y. Okay? Inside the bracket with the x affects the x variable. Outside affects the y. So we have nothing in the with here. So the x stays x, and the y is going to be minus 8. Now you might say, once again, I can just minus 8. It's really fast. Now, until we add a few lessons, then it's not as fast. Okay, so we want to use our mapping. So our point is 2 and -3. And we're going to plug it in. 2 and -3 minus 8. So our new point is actually 2 and -11. Circle the multiple choice answer, move on. Right? Or I could say, the image of this point is of the form 2, comma b, right? The value of b is, you put in the numeric response box. Or the value, the coordinates of the image point are b and c. What's b plus c? Or the sum of b and c, right? They can be asked so many different ways. So this one here is all over to the side. This is actually a horizontal translation 7 what? Right? So it affects the x because it's with the x. So you're going to get xy becomes x plus 7, right? And what's the 5? Vertical translation 5 what? Yeah. So it's going to be y plus 5. Then plug it in. 2 -3. And then 2 goes in for x, 2 plus 7. -3 goes in for y, -3 plus 5. And we're going to get 9 and 2. Okay? Why do we have to know all these basic things very, very well so that when I add ugly things into it, it's still easy? Okay? Write the equation of the image. So that's asking for the transformed equation of y equals f of x after each transformation. Okay? Horizontal translation of 5 units left. X is going to be replaced with x plus 5. We agree? If we did replacement notation. So our equation is going to be y equals f of x plus 5. 3 units up, y equals f of x, then what? Plus 3. We can put it in instantly right now, but if we wanted to do replacement notation, we'd actually have y would be replaced with y minus 3, wouldn't we? So that when we had the equation, we'd have y minus 3 equals f of x. And when we move it over, it's a plus 3. Yeah? We have a horizontal translation of m units right. So we're going to have y equals f x m units right. What am I going to get? X minus m. P units down. Minus p. If we did replacement notation, though, x would become x minus m, and y would become what? This would move over. Y would become what? Right? because we don't have any stretches right now, you could just put the y over here and you'll be safe. Once you have a stretch, it changes the ballgame, and I'll show you how when we get there. Okay. In each case, the graph of y equals f of x is shown. So we're given the original. Okay? Sketch the following transformations for each case. We're taking a graph, we're moving a graph. What do we use? Mapping, because all we're doing is taking points, moving points. Whenever we're moving points, we use mapping. So our original point is xy. It's now going to be what? X plus 2, because it's with the x. Is there anything with the y outside of it changed? So just y. So our x's are going to add 2, which makes sense, moving 2 to the right, and our y's are going to stay the same. So we'll do 1 by mapping here. So we have 1, 2, 3, 4, 5, 6. So negative 6, 0 is going to be negative 6 plus 2 and 0, which is negative 4 and 0. So my new point is negative 4 and 0. Now, if you just have translations, could we just move them 2 to the right? Yeah. But if this was more intense, we have to use mapping, okay? And you'd have to use mapping for every single point, correct? So you'd have to do mapping 1, 2, 3, 4, 5 times, okay? So we're going to move 2 to the right. The next thing I'm going to do is connect them. Why? So I don't forget which points were supposed to be connected. If you draw all the points, then it's like, uh-oh, now which ones go to where? Okay, so draw a point, the next point at a time, connect it. Next point, connect it. This one's going to move 2 to the right. Oops, 2 to the right. 2 to the right. The more points you move, the more accurate your graph is, right? So if I actually went along and moved this 2 to the right and moved this one 2 to the right, move this one 2 to the right, it would be here, right? And then I'd be more accurate. Okay, this one I'm going to subtract the 2 over first. So then I have it in y equals. So my x is going to become what? X minus 3. And my y is going to become y minus 2. So if I took a point and did mapping with it, my point is 1, 2, 3, 4, 5, 6, 7, negative 7 and 2. And I plug it into mapping, I'm going to get negative 7 minus 3 and 2 minus 2. So my new point is actually at negative 10 and 0. Here. Okay? So I'm going to move them 3 left, 2 down. So I'm just going to do that. Now, if there's more, you're going to have for sure use mapping, right? Because then it starts getting like, oh gosh, I'm moving, multiplying by this. You're going to mess up. Okay? Even 3 left, 2 down sometimes gets a little dicey. Okay? So 3 left, 1, 2, 3, 2 down. Connect them. 3 left, 1, 2, 3, 2 down. Connect them. 3 left, 1, 2, 3, 2 down. 3 left, 1, 2, 3, 2 down. So here it says state the coordinates of the image of the point negative 3, 5 under the transformations described by this. Well, this is mapping. Before we actually find the new point, I want you to tell me what the transformations are if I give you mapping, because sometimes they give you mapping and ask for the transformation. So this is a horizontal translation, 7 what? When you put it into your mapping, what do? You put in what you do, correct? So only in the equation is it backwards. Mapping, you've put in what you need. So here, remember, here we had an x minus 2. Into mapping, we put it in as an x plus 2 because we moved 2 to the right. So your mapping actually tells you exactly what you're doing, correct? So this is where I'm saying you have to get your head wrapped around it. So in the equation, it's backwards, but in mapping, you're doing what you're doing, okay? So this is actually going to be 7 to the left and a vertical translation 4 up. Mapping, you do what you say, right? You took it from the equation and made it into mapping. So our coordinate is going to be negative 3, 5, and it's going to become negative 3 minus 7 and 5 plus 4. So it's going to be at negative 10 and 9. So B, you have x, y, and it becomes x minus 6, y plus 1. So it's a horizontal translation, 6 what? Left. Because we're going, think about it as a point, correct? We are at the point x, and we're minusing 6 from it. Which way are we going? Left. Okay? You have to think of it that way. 6 left. And then we're at the point, and we're going 1, we're adding 1 to it. So we're going 1 up. Okay? Do our mapping, we get negative 3, 5 becomes negative 3 minus 6 and 5 plus 1, which is negative 9 and 6. Seven is where I told you you have to really look at the equation first, because sometimes the original equation has transformations on it already. Okay, so we're going to look at these ones. Describe how the graph of the second function compares to the graph of the first. Every single one of these you can punch into your calculator. Why? No F. Okay, so this is the original. The original has an x to the 4. So the y and the x to the 4 are all the same, correct? The only thing that's changed is this plus 3. Is it with the x? No, so it's at the back. So what is it? A vertical translation, 3 up. Now we look at this one. We have y equals 6x minus 3. What's the only thing that changed? X minus 1. That's the only thing that changed, correct? Was the rest already there? So if you told me a vertical translation 3 down, would you be right? No, it was already 3 down. It would only be 3 down if that was a minus 6. Yeah? So this would be a horizontal translation because it's with the x. 1 what? You try C and D. This one, the original, was just y equals the absolute value of x. This is with the absolute value of x. The worst thing you can do is let the equation actually throw you off. Who cares what the equation looks like? If it's with the x and changed, it's a horizontal translation. If it's not, it's a vertical, for now anyways. So here we have a vertical translation to what? Up, and a horizontal translation 6 right. Here, this changed. It's with the x, and this is at the back. So this is a vertical translation, 3 up. And this is a horizontal translation, 1 left. Don't let the wonky equation mess you up. Okay? So here they want us to write the equation of the image. So our original is y equals x squared. We have a horizontal translation 3 to the right. So our new equation is going to be y equals x what? Minus 3. And you're replacing the x, correct? So you have to have a squared up here. Because we're taking this little x, which is squared, and we're replacing the whole thing with x minus 3 and squaring it. Yes? If you put it at the back, it's a vertical translation. If you forget the squared, you went from a quadratic to a linear, which doesn't make any sense. That's the craziest transformation ever. Okay? So this one, if we had a horizontal translation, it would be up here with the exponent. So I'm going to add to this. I'm going to say and a horizontal translation 3 left, just to prove a point. Okay, So we're going to have y equals 10, x 3 left. So what's it going to be? Plus 3. Wherever the x is, it joins it. That's it. Doesn't matter where don't let the equation throw you off. Wherever the x is, it joins it. And then 2 up, plus 2 at the back. If we did replacement notation, it would be y is replaced with y minus 2. And x is replaced with x plus 3. Right? Because you would be replacing the y, so the 2 would be over on this side. So that's why you have to have the opposite. This one is a horizontal translation 4 to the left. The x is under the square root. We agree? So that's where our x is going to stay. Instead of being in brackets, it's under a square root. Instead of being brackets on the last one, it was under a radical. Instead of being under the last one, it was in absolute value signs, right? It doesn't have to always be brackets. So we have 4 to the left. So we're going to have the square root of x, what, 4? And because it's under the radical, it's with the x, okay? And then 3 down, we can put a minus 3 at the back. If we did replacement notation, it would replace the plus 3. So in this one, we have to actually read thoroughly which one is the transformed and which one is the new. The function represented by the thick line is a transformation of the function represented by the thin line. So which one's the original? Yeah, which one is going to be the original? Yeah, that's true. Of the thin or thick, though, which one's going to be the original? Thin, because it says the function represented by the thick line is a transformation, so it's being transformed, than the thin line. So thin line's original. Now, these ones are easy. Why? Because all you can have is horizontal and vertical translations. So all it can be is move to the right or the left, or up or down. After this, though, we're going to be able to stretch it, make it wider, make it reflect left, right, down, up. Okay? That's when it gets more complicated. So you have to do the basic stuff really, really well. Okay. So the thin one, oh goodness, this is the thin one. So we have to, I'm going to go from vertex to vertex because at least they're comparable, correct? So I'm going from here. So that's 1, 2, 3, 4 down. And then we go 1, 2 to the right. The original equation here, it tells you what it is. It's y equals f of x. So here's what it tells you what it looks like. Okay? They even labeled them as f of x. So we're going to get y equals f x what? Minus 2. And then at the back, minus 4. So this one is y equals f of x as well. We're going to go from here to here. So 1, 2, 3, 4, 5 down. And 1, 2, 3 right. So we have y equals f of x. It's going to become y equals f of x what? Minus 3. 5 down. Yeah. This one has only been moved 1, 2, 3, 4 down. So our y equals f of x is going to become y equals what? F of x. Now that changes because nothing does to the x. And what? Minus 1. Okay. This is our last one, then there's your assignment. Okay. So this one you have to pay close attention to because I lose people on this one. Y equals square root x is a radical function. So that's the basic radical function. Okay? We're going to learn about radical functions this year. What vertical translation would be applied to y equals square root of x so that the translated image passes through? The translation image, So that's the translated point, right? Passes through 16.7. So this is the translated point. Now, we can only do these questions because they're only giving us translations. If they gave us stretches and stuff like that, we wouldn't be able to do this. And we can also only do this mainly. We could, I guess, if they only gave us one thing. But they can only give us vertical, or they can only give us horizontal. They can't give us both, or they can't ask this question without giving us a point. Now, why is that? Well, in this case, only the vertical changed, right? So what stayed the same? X. So I know x equals 16 in both cases, correct? We agree? So my original point is 16 and something. How can I find out something? Go back to grade 10, before you're even taught about your calculators, going to your table. If you had an x, how could you solve for the y of the original equation? Plug it into the equation. So our equation is up here. This is the original equation. We're trying to find the original point. So we have x. So we're going to go y equals square root 16. So what does y equal in this case? 4. So our original point is 6,4. It becomes, 16,4. It becomes 16,7. What did we do? We went 3 up. So the only reason why they could do this is they didn't change anything about the horizontal one, right? So we had a starting point. If they changed both, they'd have to give us a point. They'd have to give us a coordinate off the first one. Yeah? So you guys are going to tell me what to do for this one. What horizontal translation would be applied? So what did they move? The x. Yeah? What did they keep? The y. So on this point, it's something and 8. And on the new, it's 17 and 8. We agree? How do we get this something? Plug it into the equation. The equation is y equals square root x. Y is 8, so 8 equals square root x. How do we get square root by itself? How do I get rid of a square root? Square it. Square root by itself. I'm going to say x by itself. Didn't make any sense. Good. X equals what? 64. So I went from 64 to 17. Did I move right or left? Left. I was at 64. I'm now at 17. I'm moving to the left, to the left. Yeah. Okay, by how many? Yeah. 47. It's just 64 minus 17. There you go. This shouldn't take you long because horizontal and vertical are easy. However, if you're really bad at horizontal and vertical, when I go to add more to it tomorrow, that's sad, right? It's not going to work out well for you. So we have to be very good at each lesson so that we're doing one new lesson today, a new lesson tomorrow, a new lesson on Friday, and then when you come back after the week, we're lumping them all together. All of the different lessons. So you need to know your stuff backwards and forwards in each separate lesson so that when I throw them all together, the stretches, the reflections, the translations, you're like, this is easy. Okay?